speakers today are Professor Ron S. Kennett, who is currently Chairman and CEO of the KPA Group, Research Professor at the University of Torino in Italy, and International Professor Associate at the NYU Center for Risk Engineering, and also Daniele Amberti, who is a functional analyst, applied statistician, and advanced analytics consultant at I4C Analytics Software Vending Company. Today, Ron, who is joining us all the way from Israel, and Daniele, who is joining us from Italy, are going to be presenting on DoE in practice, a review of basic and computer experiments using hand-on simulators. This talk was originally given as a webinar for the ENBIS, which is the European Network for Business and Industrial Statistics, and we are now happy to share it with the division via webinar. All phones and microphones have been muted except for the presenters, so if anyone has any questions during the webinar, please use the questions interface in GoToMeeting. I will hold all the questions until the end of the presentation, at which time Ron and Daniele will have time to answer some of those questions for us. So at this time, I'm going to hand things over to Ron and Daniele. And again, thank you both for presenting with us today.
Okay, good evening. Thank you. The plan is to run a presentation for about 30 minutes for Q&A. Daniele and me and Shelley Zaks talk about is based on that book. This webinar is a guided tour through basic factorial experiments, central composite designs, and space filling we do via the simulator. The pedagogical approach behind this, the general idea, is by the hands-on experience so that it's a practical approach, and the feeling for what this is about. You can go and look at the. Also has the theory for those who are interested. So, registered, were directed. These links are downloads of appendix to our book. So you can trace later on. And we will start a very basic introduction to MyStat, which is an aggregation basically covering all the material in the book, and to draw a line plot, something very simple. We'll cover and what the piston simulator is about. The piston simulator, if you are working for a hospital and you want to the design of operating room blocks, you might have a simulator for that. Chemical company, and you want to improve yield, software that simulates the reaction. You might run a simulator that simulates the car. simulator stands for something generic that can be used, and here we're using it of an educational initiative. Then we'll cover experiments with R, fractional factorial experiments with JUMP, response surface with R, and then computer experiments with JUMP. So I'm passing the mic to Daniela.
Daniele, are you there?
Yeah, I'm sorry. Can you hear me now?
Yes, I believe you might have been on mute, so if you
Okay.
don't mind repeating that section there.
Yeah, sure. I'm sorry for this inconvenience. What I was saying is that we developed a package for R. It's called the MISTAT package, and the package is freely available on the CRAN website, where you can also download the R statistical software. The package is a set of functions and data sets and scripts divided by chapter. So you will find everything is on the Modern Industrial Statistics book included in this package. I just shown how to install the package automatically from the internet. It will take a little bit longer than me if you try it now, because it will install also the dependencies, so all the additional packages that are needed to run this package. Once you have installed this package, you should load the library, the package is inside R. Now I have a problem, since it seems that using this software it's not compatible with the use of the console. It's quite strange. I will try like this. It seems that we have a problem with this example. So basically, with this line of code, we make available the library to the R software, and with this other line of code, we load a specific data set into R. The package is also have also the nice feature that have an online help associated with it. So just typing help of the data or of some functions that we have developed, you will have the help online. Okay, I suggest to switch back to Ron while I try to understand what we can do for the for the next session on R, because now we are having some problems. Minchia, che macello! Perché sta puttana non funziona?
So Daniele, if you just click Change Presenter at the top right.
Okay. So what we have on the screen is our console, this data, which is cycle time of the that I mentioned before. This file in one of the appendices. I'm going to tab. I could open any software and file. Here's the data. To plot it, so I'm basically doing what you have on your, and here's the connected line plot. Way to look at this could be to use the control chart for this data. This is an I. Here I have some more information than just the plot. The distance in which the piston was run here was 0.65. Okay. So now, about we are talking about the DoE strategy, where when system or product or a service, we initially make sure that it's producing phase. We have what we call scoping. Then we have a long list of formats. With screening, we are trying to reduce the long list to optimizing on the active factors. We are not going to classify it as inert or inactive, which basically means they don't do anything. We've gained this knowledge to make sure that what we have over time, we're going to do some robust experiments that our solution, that our recommendation is robust and with deviations in inputs and in several steps and time to achieve. If we have experiments, which means we have a simulator that we can use to reach a decision on how to run a system, then the optimizing and the basically where you gain knowledge and the robustness can be together. We are basically doing things faster. A reference to that is this paper that we published, the technology and quantitative management. This is one paper among on how to run computer experiments. So I'm giving F piston is used to demonstrate what we call which is what I referred to before. So for the 94 participants in this webinar on my screen, I'm sure this is for the big majority. I would like to cover this so that we are on foot. With DoE, that we are addressing this is an example that George Box used to give. You can look at the cage. We can look at the cage again. Nothing happens. The cage with male rabbit. You can look at it. Nothing happens. You can look at that. And nothing happens. But if both of them happen to be in the same cage, so-called interaction. This interaction, which is measured by the combination of the two factors, is presented by a two-way plot, and you can see on the horizontal male in the cage. The red and the black are the different levels of action, is represented by these lines crossing and the big angle, the angle line. In the case of the piston, we're going to have seven factors. This is from the MyStat documentation. The piston has a weight, S. There's an initial gas volume, V0. There's atmospheric pressure. There's ambient temperature. And the simulator basically allows you for the, and this is where the jump used. It basically gives an option with dials to change the setup of, and it is used to demonstrate how you would run process control projects, or how you would run design experiments. There's several used repeatedly throughout the book. So it that to run fractional factorials and computer experiments. At this point, I hope with R, and I'm going to pass this on to him.
Okay, so here we are. I hope we will not have other problems with the R installation. Just to cover again the topics we already mentioned before, here I'm executing one of the commands. So I'm loading the MyStat library. I loaded the cycle T data. Here I show the help online that we have. Going back to R now with just writing down the name of the data, we get the numbers on the console. So going on to the example of the full factorial design, here we define a list of 5 factors that we can control on the simulator. We load the DoE base library, that is another library available freely on the internet, and here we use the function factDesign which creates our full factorial experimental table. So here we need a little bit of R code to modify this full factorial table to something that we can use directly in the function piston simulation. This function runs a simulation of over the whole factorial experiment, and we add the response to the original data with the full factorial runs. So here now we can compute some statistics, for example an analysis of variance of the different factors, where we can see that we have several factors with main effects that are significant, and here we have just also an interaction that is significant. Further, we can have some plots. Here we have main effect plots for the 5 factors that we are testing, and also we can plot an interaction plot again for these 5 factors. Okay, so I hope this introduction with R is successful and not as our previous example, and I switch back to Ron for going on with the presentation.
Okay. Some problems with the voice, and I'm going to speak as close as I can to the mic. Hopefully this will help overcome some of this. Okay, so we covered you can look at the slides. If you have my starting uploaded, you can actually, and you have the code. What Daniele did is there. You just have to copy and paste it. You can just pick that part, and it will reproduce for you action plots. And the table with the analysis of the significance of the factors. So now we're going to fractional factorial, this time with jump, and we're going to use the simulator. So to fractional factorial, this is what we're going to be recreating. Those of jump add will be able to do it with me. So in the add-in, create a table of inputs. It is up here, and it's make table of inputs. And we're going to a fractional factorial. So we're going to load the factors before. So now what we had is shown on this screen. N is between 30 and 60, and it's a continuous value. We might want to and exactly at point 0.6, 5, and an upper limit of 0.7. The options we have are listed here. We're going to take, which means not all the possible combinations. We're going to generate the table. To get the response, basically running the simulator. So what we have done is, and then I get some comments. What we have done is basically design an experiment with 30 of the experimental factors that we are investigating. And this has produced for us responses, and we want to analyze those. Model, I can see what is in the script is basically and interactions. Okay, I don't even have to look at it. If I want to run it immediately, I can do that. Here is the model. I can change the model. I can delete some of the factors. This is a model up to run it, and we have here with the probabilities of the significance of the effects. The time given is to do a screening analysis, and here the effects that are significant are, so unless you're colorblind, you can see very quickly where a significant effect on cycle time show up. Now, following our DoE strategy, we've done some scoping initially. We've done so we can reduce the number of factors or focus on the fact. And now we're going to the optimizing phase through a response surface, and I'm passing on the screen to Daniele.
Okay, so now we will address a response surface example in R. What we do is to load again an additional library. The library is RSM, or a package. This stands for Response Surface Model. Here we define the levels that we want to use in this design of experiment. It is basically a central composite design, but this topic is not addressed in this webinar, so we will just go on with the example on how to use this kind of design of experiment for analyzing the data with the collected data with the response surface model. So what we need to do is to create an R structure that is somehow a data table with all the combination with the levels that we want to try. The data technically are stored in encoded form, and this is the formula. That is exactly what we have done here. It's just some technicalities needed to use this package, don't worry. So again, we need some transformation to move from this kind of coding to something that we can use inside the piston simulation function, and is this couple of lines here. And here we call the piston simulation, and we save the results into a variable with its name is PS. What's inside PS? It is basically a table with the setup of the experiments and the recorded results. This is repeated 30 times for each setup. So instead of looking at the first few lines, we can have a look to the last line. So it's a different setup if compared to this one, with obviously a different running time for the simulation. After doing this, we aggregate the results, just calculating the mean for these 30 runs, and we add this mean to our original table. So it's the design now and also this additional variable that is the response. Now we can analyze the data with this response surface model, and we say that the mean time is a function of a second order interaction between these four variables. And obviously we can call a summary over this, and we can see that again we have a significant main effects, these three, and one interaction that is significant, and also a variable that is significant with its transformation. What is interesting is also that we can make few plots. With the mean time over the different levels of the variables that we are analyzing. So for example, this is x1, this is the mean time of the cycle of the piston moving from a setup that is -2 to a setup that is 2, and again for all the variables. This variable is the one that have also significant effects that is not linear, as it is shown in this graph. We can have also a contour plot that shows the cycle time over two variables that we have chosen to plot together, and as we can see, the effect is not linear at all. And at the very end, we can also ask the software to show us the steepest descent for reaching an optimum over this surface model that we built up. So basically, as Ron said before, all the scripts are available inside the package MISTAT on CRAN, so you can try these scripts by yourself. I will move again to Ron for the presentation.
Thank you, Daniele. So we are now on the last leg of the webinar. We have minutes, and we are going to move to the most exciting part, which is the use of computer experiments, the introduction to space filling designs, which are in the last newsletter of the Stats Division, Jamie Galowski from Pratt & Whitney. Pratt & Whitney in this context. So going to continue with the piston, and now we consider that as Pratt & Whitney is doing with the engine design simulators that designing and manufacturing. So I'm going back to jump. The add-in, just to remind you, was used the levels of the 7 factors. I'm going to go now for space fit. I'm loading the factors and the which I could have changed earlier. I'm going to use a Latin hypercube. I will show you what it really in a second. Once the 70 runs have been designed, you see 70. Here's the table. Yes. Now it is waiting for the to be invoked. So now we're going to run the simulator, and we're going to get Y's, in other words, cycle times for this. So I said that I would show this filling experiment looks like. In this case, this Latin hypercube. Well, if I combine the factors as they were designed in this experiment, it's called space filling because it basically fills a space of each factor against all the others. So based shotgun experiment, it's filling the space on each of these dots a value from the simulator, and this the analysis is done with and Gaussian processes. Sometimes this is called kriging. This is called DoE. All this is explained in our book. I'm not going to model here is automatic model for the analysis of the data. So we're going to use the cycle time versus MS V0, K, P0, P0, and T in this layer. So if I run this, okay, I'm going to get several outputs. I can ask for a profiler, giving me the marginal impact of changes in M as I change it, and I can see also that the interactions are playing because things are also changing. I change M. If I want to indicate what I was after, which is 0.6, I can set up a desirability function which will have a maximum value exactly at 0.6. So here I can set this also. I can parameterize it. I can do it. Below, you see the achieved as you change the factors, and we can see here that when you change them, nothing happens. The last, I can see the impact of variability in these factors driving the variability in the response and in the desirability. So for the robustness, I can use a simulator, play with random factors. I can do that and have different ways. And basically, this is a simulator which picks different values of S, V0 it through the profiler, which is representing derived through this Gaussian process modeling that we did. This variability is transferred into the variability of the response and in the desirability. Again, the book is going through all this, of a book that we published in 1998 for computer experiments. We did not have it in the 1998 book, but also available in Spanish and in Chinese, in case this is of interest to anyone. Another book, or it's actually 4 volumes, to the topics we cover today, is this encyclopedia of stability that I co-edited with Fabrizio Ruggeri and Fred Foltin. Computer experiments. Here you have an entry which is 3 pages. Obviously, all of this is available by simple Google. So, photo 2, and I think we are just on time. I pass the mic to you now.
Okay, we do have 3 questions.
Okay.
So the first question here is, can interactions between factors be considered as lack of knowledge? If one understood design adequately, would there be a more appropriate main effects model?
Wow, that's an interesting question. I think it's actually just the opposite. If you understand the interaction, advantage of them, and because you can understand where you should changes in one factor are not going to impact the response. I would say it's the opposite. The understanding of interactions is, to improve the system that you are studying, which is actually is to get a good system. So I don't know if I answered that.
Okay, and the next question that we have here is from the same attendee, and
Yes.
the question is, screening can throw out important factors affecting variation. Is optimizing generating a polynomial equation with no physics or chemistry, is just being able to regenerate the date enough?
Okay. My view on this is that a very practical, hands-on approach in an academic institution where you are studying, you're doing basics. You want to go forward. You want to go forward in a reasonable way. Validate your findings. You verify that you are on the right path. Might indeed mislead you. Very rough model. You are not picking up, but practically to do everything, you're not going to do anything. So it's like a funnel. And that the question is rightly put. You should be ready to really your assumption. So if things don't work out, you might have and do another phase of if you have contextual and the physics, you understand the chemistry, you understand what is now called mechanistic. That knowledge should be used in how you design the experiments. And how to combine empirical designs with mechanistic modeling knowledge, mechanistic models. This that is playing a very important role in pharmaceutical and I think there are some advances in this area. I have a paper with John in the ASA biostatistics 2 years ago, I think, where we are discussing some of them.
Okay, thank you, Ron. And the last question here is somebody asked if the R script for the factorial design is included in the zip file.
The R script, yeah, everything that you saw is in. You can download it from CRAN. So when you upload my dependencies, everything is quote. You don't have to additional packages. It's all brought together and integrated on the with our scripts. What Daniele showed is there. So we'll copy and paste the part. If you don't want, if you run the whole script, it will run by chapter. Everything that is in the chapter. The scripts are organized by chapters. If you want part, you can paste the part that you're interested in. You get some experience with R. It's actually quite easy. Programming, but it's not really programming.
Okay, Ron, thank you for those answers. And I don't see any more questions on the questions. Oh, okay, we do have one more that just popped up. Let's see. Where is the relationship between variability and response? Is it assumed constant variance at all levels of the mean response, and is this realistic? And that's kind of a loaded question.
Okay, okay. I refer to this idea of a stochastic emulator. In the stochastic emulator idea, with phase where you fit using a Gaussian process, as we've done, and to pick up variability, you're running another set of experiments where you use this model or the Gaussian process model to generate points and variability around that surface. In that process, you don't, it's fixed. Variability is different. Actually, variability is represented by a surface which shows you where you have low variability. So in that case, not assuming the variability is fixed. I don't know if that was You know, the analysis of variability comes in, and where the robust experiments come in. Okay, that's related to the Taguchi. We didn't cover these here, but if you go or in our book, you will see also that phase of the experimental design strategy where around just to make sure that when you set these parameters, when operations to work around specific values, it is doable. It will withstand variability in the inputs and not be very sensitive. If you are suggesting an optimum, but it's like a very thin peak, you're going to fall off, and that's not what you want to do. But is an important part. Is what I called building.
Okay, and I think we just have time for this last question. And I think some of this might have been captured by the answer that you just gave, but somebody asked the question, said, is the uncertainty a bit high in the Latin hypercubed? It seemed that the uncertainty in the responses was so high that it was not actually useful.
I assume this is in the specific example, it's not a generic that we gave. Do you interpret this as the general question?
Yes, in the specific example.
The specific example is actually quite, if you look at the initial line plot, you can see that is not behaving smoothly. It's sort of chucking. It's going fast and slow. Okay, and that's also shown in actually what these are quite standard situations to deal with. To be provided is something, an easy with the things to see what the impact is, and software, statistical software, you can actually run iterations, basically work in a lab environment. So yeah, we have not reached the end of the road in this example. It was just to show parts of the journey that you are taking until you end with in terms of how to design the system. That paper, the QT paper, is comparing different ways to do that. How different strategies provide different answers. That paper, by the way, QTQM is open access, so anyone can. Technology and Quantitative Management is a journal which is open access, so don't need anything just to find it. If anyone is looking for the link, glad to provide it.
Okay, excellent. A couple of quick things for those of you who are still on the line. We will make this presentation available for later viewing on the division's YouTube channel, and we'll do this as quickly as possible, hopefully by this evening. So if you want to rewatch the presentation or share it with a colleague or coworker, The division's YouTube channel is just youtube.com/ASQ Stats Division. So youtube.com/ASQ Stats Division. And I think if there are no more questions, we will go ahead and end the presentation. And Ron and Daniele, maybe if some of the attendees want to contact you via email for some more discussion later. Otherwise, we thank you again for presenting with us today. And I hope everyone on the phone enjoyed the presentation. And we will, of course, have more webinars in 2014. We'll announce these on our LinkedIn group page as well as the email newsletter and our website. So thanks again, Ron and Daniele, and I hope everyone has a safe and happy holiday.
Happy New Year.
Happy New Year.
Thank you very much, and thank you.